going to start here. Excuse me. I'm going to start with this quick activity here. This is something you guys can do with a partner or even a group of 3. I'll kind of give an example here. And the way this is going to work, choose a whole number between negative 150 and positive 50. Don't choose the same number. I'm going to be lazy and pick the number 0. And apparently have trouble drawing it on here. Let's try again. And still, here we go. 0. And my second number is going to be the number 1. Lovely. I now need to put the symbol in here. And we're going to say, what's this going to be? Well, 0 is less than 1, so less than 1. Lovely. Alright, so now, operation applied. Let's add 4 to both sides. Alright, so we add 0 plus 4 is 4. And 1 plus 4 is 5. Symbol stays the same because 4 is still less than 5. Did the sign change? No. Alright. Next operation. Okay, again, we have to always go back to the original equality. You can read that over and make sure you read the rules here. We're going to multiply by, I don't know, let's pick 4. 0 times 4, still 0. 1 times 4, still 4. I guess not still 1. But 1 times 4, and guess what? Our symbol stays the same. Did the sign change? No. Alright, let's get down just a little bit here. Oh, we're going to have the same fun that I have on the smartboard. Remembering back to my original symbol was 0, and it's less than 1. We added 4, we multiplied by 4, nothing changed. No. No. Alright, let's divide by 4. Okay, we're going to cover all our bases here for a moment. 0 divided by 4, still 0. 1 divided by 4 is 0.25. Guess what? My symbol does not change. Let's subtract 4 from both sides. 0 subtract 4 is negative 4. 1 subtract 4 is negative 3. Guess what? Negative 4 is still less than negative 3, right? If it's minus 4 outside, it's colder than if it's minus 3. Not by much, but it is. Okay. Let's try something different. What if we've added and subtracted? We've multiplied by 4 and negative 4. What if we multiply by a negative? So multiply by negative 4. I'm just putting the negative 4 in brackets so it doesn't look like I'm trying to do multiply, subtract 4. It's multiplying by negative 4. So 0 times negative 4. Guess what? That's still 0. 1 times negative 4. Oh, this could be interesting. Guess what? 0 is bigger than negative 4. The sign changed. Yes. Okay, what if we divide by negative 4? Now, the reason this is enough is if I'm adding 4, that's really the same as subtracting negative 4. And if I'm here on this one here, if I'm subtracting 4, that's really the same as adding negative 4. So I'm really covering all my bases here, at least with 4. You can try this, and I want you to try this with your own set of numbers, and don't use 0 and 1, and also don't use 4. Maybe try starting with some negatives. 0 divided by negative 4 is still 0. 1 divided by negative 4 is negative 0.25, or I guess if you're wanting to be fractional, it's negative 1/4. Negative 0.25 is less than 0, or 0 is greater than negative 0.25, and so yes, it does change. Right, this is important. Hopefully we've maybe learned something. And we're going to move on. I want you to try that, pause it, try that with your own numbers real quick. What are the two operations that will change the direction of the sign? You should be able to gather that from what we just did. I'll let you try that out and see if you can figure that out. Keywords, solution of an inequality. When we talk about solution of an inequality, simply what we're looking for there is we're trying to say, okay, if we're looking for the solution of an inequality, we're simply looking for the values that make it true. And if it's, if x is my variable, so it's the values of x, but the values of the variable that make it true. So if I tell you, I'll get you to write this down here, but if I tell you 2 times a number is greater. Alright, so solution of equality, the values of the variable that make it true. Alright, let's take a look here at how we can deal with this. So we want to isolate the variable. This is going to look a lot like algebra. Alright, x minus 3 is, in this case, greater than or equal to 2. Okay, lovely. Going back to my out loud example, say 2 times a number is greater than 3. 2 times what would give us 3? 2 times 3 equals 3. So as long as the number is bigger than 3, my original inequality will be true. In this case, we're looking for x minus a number is greater than or equal to 2. All right, well, let's get the variable by itself. How do we do that? Well, we're subtracting 3 from the x, so let's add 3 to both sides. And so we're left with x is greater than or equal to 5. So this is going to be true for all values of x that are greater than or equal to 5. You can try it out with 5, right? 5 minus 3, is that greater than or equal to 2? Well, yeah, it's equal to 2. What about 10? Well, 10 minus 3? Oh, yeah, that's 8. That's 7, sorry. That is definitely greater than 2. Okay, great. We're good to go. Moving on to this one here. Okay, we want to get x by itself. Well, x divided by 3. Okay, we got to multiply both sides by 3. Okay, so 3 times x divided by 3. These cancel. I'm left with just x. 3 times negative 5 is negative 15. I multiplied by a positive, so I don't have to worry about reversing my sign. X. This is true for all values of x, where x is less than negative 15. So, will it be true for x is equal to negative 15? Let's try it and see. Negative 15 divided by 3, that is equal to negative 5. Negative 5 is not greater than negative 5. So it doesn't work when x equals this, but that's not my inequality. Let's pick a nice number, negative 18. That is smaller than negative 15. Negative 18 divided by 3 is negative 6. Negative 5 is greater than negative 6. It works. All right. Moving along to our next one here. Here, I'm going to isolate my variable. Okay, I've got negative 2x. That's multiplying, so I'm going to divide by negative 2. Divide by negative 2. And I'm left with x. Now here we got to be careful. We flip the sign because, again, just like you should have discovered back on the first page, when you divide or multiply, but in this case divide by a negative, the inequality flips. So I'm left now with x is greater than negative 4. So let's pick a number bigger than negative 4. Like, I don't know, something's easy. 0. Okay, good. Negative 2 times 0 is 0. Hey, 0 is less than 8. Perfect. Okay, let's pick another one. Negative 3. It's greater than negative 4. Negative 2 times negative 3 is positive 6. Hey, 6 is less than 8. Must work. All right, your turn. Pause the video. Take a look at the show you knows. Okay? They're pretty straightforward. But take a look at them, give them a try, then restart the video, check your answers. Make sure you pause it. All of you. Pause it. Come on. All right, here we go. Sorry, we don't need to copy the sign right at this point in time. Okay. Here I'm dividing by a positive, so I don't have to flip the sign. And I can write it like this. That's perfectly legit. However, a lot of you are probably going to want to flip this around so you can say x is less than negative 2.5. And that's fine too. Just make sure that when you flip it, like reverse the order of the equation, that you also reverse the sign. So the 4x, if we start at the beginning, is less than negative 10. This one here, we're going to multiply both sides by negative 8. Ooh, we're multiplying by a negative. That tells me I need to reverse the sign. And these go away. I'm left with x is not greater than, less than, because I multiplied by a negative, 24. Right. Excellent. Moving along. Verifying solutions. Everybody's favorite part. Although in this case it's not really too bad. So Trevor was asked to solve this inequality. Negative 2x is greater than or equal to 11. He represented his solution. X is greater than or equal to negative 5.5 on a number line. There he is. Your job, let's verify if Trevor knows what he's doing or not. First of all, we check the boundary point. Now, when we check the boundary point, all we're doing here is we're basically treating our original inequality as if it's an equation. And so we're going to check to see, did we actually get that boundary point correct? Is it actually negative 5.5 or did we do algebra wrong? Okay, so the first thing we want to do is we're going to say, okay, we're going to assume negative 2x equals 11. Let's plug in negative 5.5 for x. And I'm not, so that's kind of, we're assuming this negative 2x is equal to 11. But what we're going to do is we're going to do the same thing we've been doing here, left side and right side business. Okay. And the left side is negative 2x. And the right side is 11. So we negative 2 here. We're multiplying by negative 5.5. 11. Yay. Our boundary point is good. So we did the algebra part right anyways. We still don't know if the direction of the inequality is right, but we do know that the boundary point is correct. Okay, so that's checked. Move on. We want to check that the inequality symbol is correct by substituting some possible values for x into the original inequality. So the original inequality, write it down here, negative 2x is, oh, sorry. Good grief, let's go. Negative 2x is greater than, I was going to write that backwards. Good thing I checked. 2x is greater than or equal to 11. So we solved it and we said x is greater than, bigger than negative 5.5. So let's pick a nice number, right? I could pick negative 5.1875. but that would sort of make my life miserable here. Let's try a nice number like, oh, I don't know, -1. So we've got -2 and -1. And we're comparing that. Okay, so this is our left side. Here's our right side. I'm leaving the inequality at the beginning just so that I can see that this number on this side here should be bigger than 11. So 11, I think you can already see we're going to have a problem. 3 and 11. Is 3 bigger than 11? No, it is not. Which tells us we made a mistake. Or I should say, sorry, Trevor made the mistake. So if we will go back here and look at what Trevor did, he divided by -2, but he didn't flip the sign. And so he made a mistake. His inequality is pointing the wrong way. And so really what he should have is, as a solution, is x. Boundary point is correct. X has got to be less than or equal to -5.5. If we'd go back and check that and pick some number like, I don't know, -10, that's a nice one. So we've got 2 times -10. That's going to give us +20. And guess what? +20 is, going back to the original inequality, greater than or equal to 11. So now when we realized, oh, there's my mistake, my boundary point was still correct, I've gone back, I've corrected the mistake, there's my correction, I do the recheck, and now it works. Well done. Okay, moving ahead. So you verify, here's your 2 steps. Check the boundary point, substitute values in to see if the inequality symbol is correct. Make sure that the arrow is going the right way. So here's, I've given you problem and solution. Your job, check it for me. Okay, so pause it, do that. Okay. Excuse me. You've paused it, lovely. Let's verify the boundary point first of all. So if I say let's do this the right way. Left side and right side. -5x over here. +30 over here. -5 multiplied by -6 is indeed 30. That's good. Boundary point is good. Okay, we've done that part the right way. Good. Now we're going to substitute values in. Okay, we're saying x is less than -6. Again, pick a nice number. -6. -10 is less than -6. Okay, let's check that out. Okay, so left side. Right side. Again, we write down our original. -5 is less than, -5x is less than 30. Okay, so x has got to be less than -6. Alright, good. We're going to pick -10 because that's a nice number. Okay, so we look left side and right side. -5 times -10. Uh-oh, this is +50. Is +50 less than 30? No, it is not. So +50 is not less than 30, which means we've made a mistake on the direction of our inequality. And we did the same problem that Trevor just made up there. We divided by -5, but we didn't flip the inequality. So my answer actually should have been x is greater than -6. And again, if I pick something greater than -6 for my x value, like, I don't know, 1, that's bigger than -6. -5 times 1 is -5. Is -5 less than 30? Absolutely. So that's what my solution should be. Alright, finally we make our way on to a problem. So, game stores offering games on sale for $12.50 including tax. Sean has set his spending limit at $80. How many games can Sean buy and stay within his limit? So what does Sean have to do? We're going to say let n equal the number of games that he can buy. Ooh. It's a pretty simple inequality, but sort of makes sense. And now we're going to say, okay, each game is $12.50, so 12.50 or just 12.5 n has to be less than 80, right? Because each game costs him $12.50, and whatever number of games he buys, the total, that number times $12.50, has to be less than 80. So let's solve the problem, okay? I'm going to start up here because I can't scroll down once I've started writing. I'm going to divide by 12.5. Lovely. Divide over here by 12.5. And I'm going to come up with a weird value, in a way, when you start thinking about it. In this case, I got 80 divided by 12.5. And if I can make my calculator cooperate, 80 divided by 12.5 is 6.4. So he has to buy less than 6.4 games. Now, perhaps you've never thought about this, but it is actually impossible generally to buy 0.4 of a working game. I suppose if the game, you downloaded only 0.4 of a game, it would work. It actually wouldn't work at all. So in this case, the interpret the solution is realizing, oh, I can only have a whole number of games, which means how many can he buy? As long as he buys 6 or less. So Sean can buy 6 or less. His maximum would be 6. Alright. And I believe we've got a little show you know coming up. Lovely. Something for you to try. Yvonne is planting trees as a summer job. She gets paid 10 cents a tree planted. She wants to earn at least $20 an hour. How many trees must she plant per hour to reach her goal? So she wants to make more than $20 per hour. She gets paid 10 cents per tree. So let's pick a nice number. Let's call, I don't know, an inequality. And we're going to say n equals number of trees. Trees. And what she wants is she's going to get paid 10 cents for each tree, so 10 cents times n has to be, if she's going to make at least $20 per hour, greater than, ooh, that's a terrible greater than sign. Let's make it better. Greater than or equal to 20. That is also not a 2. Let's try again. There we go. Okay. Divide both sides by 0.10. Divide by 0.10. And my solution is going to work out to be n is greater than or equal to 200 trees. So she needs to plant at least 200 trees per hour. So she needs to move along pretty quickly. Any restrictions on the solution? No, not really. There might be a case where, just like our video games, it has to be a whole number of trees. I guess that would be the one thing, right? She couldn't plant 200.5 trees. If you plant half a tree, you've probably killed that tree and it doesn't count. So restriction would be whole number. And so solve the inequality. We've done that already. At least, so she needs to plant more than 200 trees. Lovely. This takes us on to key ideas. Solving inequalities is similar to solving equations. It's like the same steps. But you must remember to reverse the sign when multiplying, timesing, multiplying. Please use multiplying. Or dividing both sides by a negative number. To verify the solution of the inequality, you must check the boundary point. Okay, this is exactly like what we did, boundary point stuff, with checking equations. Boundary point. It's an RY at the end of boundary. And we want to check the direction of the original inequality. So you always go back to the original one by substituting specific values. And pick nice numbers for this. Even if the inequality is all like fractions and decimals and nasty things like that, you don't have to pick those things. You can pick whole numbers. And your assignments. Maybe. There we go. You're going to try to do both days worth. Thank you. Enjoy. See you on Wednesday.